basic thing is chemistry. He has been working on various different fields, shows how interdisciplinary, and all of them demonstrate the cutting edge part of his work. In discussing, we looked at markers for tumor, two looking at water related and energy. So it's a confluence of various different areas. So we're so glad to have you here. I was really not sure what the title was. Fits very well, remediation. Few groups here, campus and also in our department, do work somewhere related to remediation. Any so with that I'll welcome tonight.
Yeah, just before starting your research related stuff, I think it's very important to thank people who are responsible for what I am here today. They are the ones, they go to lab and do experiments and get me the data and release the publications and related stuff. I think I'm thankful to them. We don't have a big team, but I think very effective and very accurate team. Then obviously I have internal some other setup issue. Okay, right. So I do have internal interdisciplinary departmental level collaborations. So obviously a lot of external collaborators all over the world. Without money, we can't do much. So funding agencies, I'm thankful to them. So just to give you a holistic perspective about my group, we are basically porous materials and functional membrane lab. They go together because functional membranes comes from porosity of the material and functionality attached to it. And we work on the new chemistry, new material design. We call it as molecular engineering of materials. And then obviously we are using into, as I mentioned, a lot of chemical conversions, electrochemical storage, and desalination. Okay, some of the stories I will be sharing. And also we work on capacity deionization. That's nothing but electrochemical um, desalination or water purification system. And also when I say we are applying these materials, we are applying them in different macroscopic forms, either powder, films, membranes, so on and so forth. Okay? The reason I'm showing the group web page because I will be sharing very representative examples here, right? So if you are interested, if you want to see, I think science has been very interdisciplinary these days. There is nothing called absolute chemistry, absolute physics, or absolute mathematics or biology. So I think who knows? So if you look around, look into the publications of my group, you may find some common interest. And obviously, I'm very, very happy to discuss or collaborate. So the whole story about this talk is about porous material. So when you think about porous materials, porous, but there are two different types of pores. One pores are quite random. There is no control over it. You have different size, different shape. Generally, in material people, I think Professor Praveen can understand, we call them amorphous material because we don't have control over it. But another type of pores, you can make them very systematic, very ordered pores. What is the good thing about this? You can control. You can have the control over it. So in our material science part, we talk them as crystalline polymers. We're talking about polymers, that's why crystalline polymers. So porous materials are not something new Dinesh talking about, right? I mean, it has been there for a while. And first to go with, I think, porous carbon. The good thing about porous carbon, obviously engineering people may like it or end users like it because it's very cheap. Right? But there is a cost for that, right? Because they are cheap, but they are amorphous. As I said, you have very little control over their porosity and surface area. So another thing is porous carbon, you cannot do too much functionalization chemistry-wise, right? If you think about it. So then there comes something called zeolites. Have you heard about it? I'm sure you did, some of them at least. Zeolites, don't worry, the number sounds very old, 1756, but this is natural occurrence. But the real research on zeolites started after 1976 when the real zeolite structure was elucidated. Okay, after that, people started, I think before MOF came into picture, zeolites membranes are the real leaders. Even today, in some of the places, zeolite membranes are real leaders. So what is the issue here? They are crystalline, nice, well and good. They have ordered pores, but they have very little functional tunability. What does it mean? Because you have to have a proper combination to get the structure there. Okay, so you have little control over that. And because of the presence of metal atoms, their weight density is high. I'm talking about gravimetric density. Okay. Then there comes in 1996 metal organic frameworks, and later 2005 covalent organic frameworks from the same group, UC Berkeley, Professor Omar Yagi's group. He got Nobel Prize. I'm fortunate to have very close collaboration with him. This is the photo when he visited my lab last year, just I think 2 months before the Nobel Prize. Otherwise, I would have been paying maybe some dollars to him, but it was free visit, right? So what is the difference here? When I say metal organic, I think if you're engineering background, obviously you have general chemistry knowledge. Right? Metal organic, when I say it's a coordination bond. Covalent organic means I'm talking about covalent bond. But covalent bond in our classic textbooks, it's a classical covalent bond. They are irreversible, right? So if you have an irreversible covalent bond, there is no way you get crystalline structure. Why? Because crystalline structure needs an error correction. Okay. So when I refer to covalent bond, I'm talking about dynamic covalent bond, which means at least in one step of the mechanism, you have a reversibility. That's where error correction happens. Okay, just to make sure. So what is the difference here? As I said, obviously they are crystalline. Both are, I would say, MOFs are better crystalline than COFs. They have ordered pores. Here, moderate functional tunability means you have to choose metal node. Accordingly, you have to select the organic building block. Of course, you have a big library there. I think more than 50,000 MOFs are out there. But if you see, and if you really narrow them down, then the metal nodes are not many. You understand? It's a very much limited metal nodes there. So that's why I'm talking about the functional tunability. And another thing with these MOFs are, again, because of the presence of metal, people are having their own perspective about this, but I think people are still having an issue using MOFs, especially for water purification, for two reasons. One is metal leaching and toxicity related to that over the time, not in a couple of cycles. So on the other hand, here, when I say covalent bond, you have an organic building block and you have organic linker. Both of them can be tunable. You got it? That's why you have higher functional tunability. And second thing, because of the covalent bond, they are much more stable, especially in hydrolytic conditions, right? And another important advantage when we talk about covalent organic frameworks, you're just talking about carbon, hydrogen, and heteroatoms like nitrogen, oxygen, sulfur, whatever it is. So they're all light atoms. So you have that gravimetric advantage. Why it is important when you talk about porous materials, you want to use it for, say, purification for the given volume of the material, right? Given weight of the material, the area which you can cover is higher if you take equal amount of MOF and COF. You got it? So that's a big advantage, especially if you want to miniature your process. Okay, that's very important. So with that, I will be focusing obviously in our lab. We are working on MOFs also, but we work on conducting MOFs, very niche area. I'm not using MOFs for water for a reason. So we will be talking more about covalent organic frameworks today. Okay. So then you may ask, okay, there are so many materials out there. Why do you care about this material, right? That's the question you may ask. If not you, funding agency will ask, right? So what is the beauty of this order structure? So think about it. I told you pores, right? Ordered pores. You can control the pore size. That's very, very important for separation application. Okay. Not only that, you can control the shape of the pores. Why do you care about it? Because shape of the pores decides the diffusion coefficient. If you think about the flux, if you think about the separation, that's very, very important features to have in your material. Then you can have the functional tunability on the surface. And also generally these materials are 2D in nature. They stack by stacking and they make 1D channel. These 1D channel inside also you can do the functionalization. Okay, you have that luxury. But most importantly, being engineer, you would appreciate there are so many materials in atomic form or small molecular or powder form, you can achieve this kind of functionality, but it's not easy to take them into macroscopic architectures like membranes, sponges, films, nanosheets, so on and so forth. But we can do that with covalent organic frameworks. I think that is the beauty of it. Okay, so when I say this, we can take this atomic features into macroscopic domain. You understand? I can translate directly. That's very important for the application. So when I started my independent career, if you look into the COF related literature, most of them are related to 2D COFs. Okay, they are made of rigid monomers, planar, so that you can have nice in planar growth. Okay, that's how you control the orderness. Right? But generally, if you see any papers, big papers, high-end papers of 2D COFs, usually they show beautiful pi stacking because of that 1D channel. That's pictorial. In reality, most of the time either eclipsed pores or completely blocked pores. So think about it. You want to use a 2D material with the ordered structure for what? You want to have that channel. So that's not really the case in most of the cases. I'm not saying absolutely. Okay. So then what we thought, can we use spatially 3D building block? When I say spatially 3D building block, when molecular level connection happens, it happens through 3D. Okay. Then what is the benefit of it? You are introducing the third coordinate, X, Y, Z, right? Then you can achieve flux from 3 directions. For flows, it's a free flow system. Okay. So we thought, can we do that? But there is an issue as a material chemist. First of all, getting crystalline polymers very challenging. Getting 2D is still okay. Getting 3D crystalline polymer is very, very difficult. Okay. When I started my career, maybe hardly 5 or 6 papers out there. All of them are in powder form. When my first postdoc joined from, I think, one of the COF leaders in the world, Rahul Banerjee, from NCL then, now he is in IISc Kolkata. So I asked 2 fundamental questions to him. but very challenging questions. Not just synthesizing 3D COF, can you make a 3D COF film or membrane? That's even more difficult because translating nanodomain crystallinity into a microscopic or macroscopic structure is even more challenging. That is first question. And second thing, I asked, can you change the physicochemical property of this membrane without doing anything in the building block stage? Usually, if you're working in a membrane, what do you do? If you want to introduce functionality, what do? You do the post-synthetic functionalization. You have to use chemical, there is a blockage issue, there is a side product issue, there is no control over functionality, a lot of issues. But what I asked him, can we start from beginning without doing anything? Let's get from the same building block, different property for the membrane. It sounds really fancy, but it's not easy, right? So it took a lot of time to achieve that. So we started with something called 3D building block itself. But if you are a chemist, if you look into this very famous molecule, macroscopic molecule, calixarine, you may have heard about it. Another molecule got Nobel Prize some years ago. So when you think about this, is a beautiful molecule because it has a cavity, inherited cavity, and cavity has a different size. And when you make it into a framework, you have a framework pores. I call it as pores within pores. You understand? That's the situation we are creating. But the thing about this one, another beauty, you can change this cavity size also by going to an higher homologs. Okay, from 4 to 6 to 8. It's the connecting units number. Okay. So what we thought, can we use this for COF synthesis? But the problem is it has so many conformers. You know, if you're a chemist, it can go to different shapes. And the time required to get into one shape to other conformer is really small. So you have to kinetically trap a single conformer to get into a structure. Okay, that's where we used our synthetic strategy. Obviously, we used different synthetic strategy. In one case, we took it. We used a liquid-liquid interfacial synthesis. Okay, you took one of your linkers into the calixarine-based one into chloroform and benzidine, the C2,2D linker, into water. Okay, because it's protonated. That's why it can be soluble in water. This is interfacial synthesis because you are expecting your membrane or film to form in between this interface. In other case, what we did is the classical approach, high dilution solothermal synthesis. Okay, the same building block. To our surprise, what happened when we used this infinite dilution condition, we end up getting a kind of nanospheres, but they are nanospheres made of 2D film. Remember, I started with 3D monomer. Okay, that's surprise because you're going from 3D monomer to 2D structure. That puzzled us. Okay, and on the other hand, in this case, we end up with very nice nanosheets, or you can call it as film. Okay, then we want to understand, because that's the part of material chemist I am in, right? So we have to understand real structure. I know we have always, there is a saying, as a scientist, we do care about why it is happening. As an engineer, you just care about it has to happen, right? So as long as it works, it's fine, right? How it works, later problem. So we are trying to understand that. And when you did this reaction interfacially, we end up getting a structure is called catenated structure. What does it mean? They are intercalated each other. By doing so, what is the change coming here? The pores within this intercalated space are much smaller. Okay. And on the other end in here is the AA stacking type. You have a 2D chain, another 2D chain coming, and they're stacking together. Same monomer, just a methodology change here. Okay. But having said, in both cases, 3D monomer leads to a 2D COF. I think that's the first case where you start with 3D monomer, you are expecting 3D COF, we end up getting 2D COFs. I think that is the reason this work got into JAX. Okay. So just to show you how really the structure forms, if you are a structural chemist, maybe you would appreciate this video. This is what happens. When this molecule comes, don't worry, it's not long video. Just it comes. Definitely it's more attractive than my talk, I guess. So they come, they hug each other. That's where this intercalation happens. Okay. then they start to grow in a 2D manner. It's like X, in different direction it starts to go. Right? So then the question came, it's a beautiful, as a structural chemist, it's something really interesting, but I'm in a place where they ask application for everything. If you go with the fundamental science, there is no value there in Middle East. So what we thought, maybe a simple proof of concept applications we had to show. Maybe one of the problems you all know, if you are working in water remediation, the textile dyes getting into the water, they're highly toxic in nature. When I talk about textile dyes, it can be anionic, it can be cationic, it can be neutral, it can be a mixture of everything, right? So this is the problem. Color looks beautiful, but this water is not so great, right? So what we thought, can we use our system for that? Before doing that, we did some theoretical calculations. We understood that the space created by this intercalated structure can lead to a specific host guest chemistry. Okay, that was the motto behind it. So then we did different dyes, as you can see, anionic dyes and cationic dyes. If you look into this anionic dyes and cationic dyes are taken very quickly within few seconds. Okay, but on the other hand, anionic dyes are not taken. If only pores are involved, both the dyes should go in. And first of all, guys, removing dyes is very important. If you can remove dyes selectively, you can think about recovery also, because dyes are again useful. Okay, so what we thought, wow, not only removing, we are selectively removing. It's a bonus. Okay, so then we try to understand that, but this is individual dyes. These are all individual dyes, right? It's easy. So what we thought, can we do it in a mixture? In real case mixture. When you see there is anionic dye and cationic dyes, in that case also it is very, very selective to only cationic dyes. Okay, but then try to understand what's happening here. If you can see in the pH conditions, what we are talking about, in most of the pH range, the zeta potential is, as you can see, is negative, right? When it's negative, obviously there is electrostatic interaction towards cationic dyes. I think that is the key. But that is not the only thing. When we did the MD calculation, please go through the article. The space between this catenated structure is really good fit to these cationic dyes, and then obviously interaction leads to the selectivity of this dye, right? So that is the first thing to tell you that the simple modification in the preparation of material itself can lead to very specific application. That's one of the stories. Then we moved on because we started by thinking our life will be easier if we start with 3D building block and we end up with getting 3D COF, but story was different. And then we really started with the 3D tetrameric building block and C2 2D linker. This is interesting if someone is working on synthesis, okay? The idea was, I told you in the beginning, you want to get 3D COF macrostructure, okay? So we were trying different conditions. In one condition, this is again liquid-liquid interfacial synthesis. In one condition, we used water ethyl acetate. Other condition, we used chloroform water. Same building block, same linker. We end up getting two films, you call it, or membranes, whatever. I think I would call it films. In one case, it's a super hydrophobic membrane. In other case, we end up getting hydrophilic membrane. Same building blocks, nothing has changed, only methodology has changed. Okay? And then we couldn't understand in the beginning. Then what we did, can we do the same synthesis in soluthermal condition, not interfacial condition? And then we end up getting this, and this is again hydrophilic. A very specific case where ethyl acetate water combination interfacial synthesis lead to hydrophobic membrane. Okay. So then we try to understand, to cut short the story, what we did. When we use ethyl acetate water system, we are introducing more defects into the structure. When we introduce defects, what happens? When you introduce the defect, this bromine atom, the unreacted bromine atom, the bromine atom within the defected area is exposed out. So that's where hydrophobicity coming into the film or membrane. Okay. So on the other hand, in other case, we have less defect. Obviously, it's relatively hydrophilic in nature. How to prove that? Because we want to prove that bromine is responsible for this, right? What we did the same synthesis using the C2 linker without bromine. That's the control experiment. And we end up getting hydrophilic membrane. right? So it tells you it's not just about creating defect, but we need to have that bromine out there. Okay, so that's how we end up getting that. Beautiful. We have hydrophobic membrane. What can we do with it? As I said, I'm coming from Middle East. Demulsification is very important application because they dig a lot of oil from the earth, right? You will have oil water mixture. So to check what we did, of course, we tested both hydrophilic and hydrophobic membranes. But if you can see, the organic hydrophobic solvents are really passing through this membrane. Obvious, right? Hydrophobic interaction, but relatively hydrophilic solvents or protic solvents are not a good candidate to pass through. And then obviously we did oil water mixture, as you can see the droplets here, and we changed the composition. And when we pass it through this film, it's very clear. Okay, we did it for academic interest 5 cycles. And obviously we got this cover article from Engavante. That was the story all about. But the question is, if you are an applied scientist, this is a beautiful science and it's a good paper, right? But can you really use it for real application? Maybe not. Why? Because the 3D linker, what we are using, 3D building block, is really expensive. We cannot get into the membrane and go to a commercial person to replace that, right? So what we thought, how to make it really, how to broaden the application prospect of that, right? So then what we did, of course, we synthesized same COF, okay? Then we mixed this COF, very small percentage, I will come to that, less than 1%, okay? Within the cellulose acetate membrane. Cellulose acetate membranes are very cheap and very easily you can make it, right? Make them. So we mix them. What is the idea here? We want to use the property of these COFs, but in a small quantity. How can we use it? We can use them as a nano pillars. Okay, that is the idea. So we did that, and of course, this is the schematic to show, and we did all the characterizations. I'm not going into details because of the time. What we did with this, we have this membrane now. I would call it is a mixed matrix membrane, right? So we use this for phenol removal. Why phenol? Phenol is very toxic chemical. It's a very small molecule. It can really pass through the existing purification, membrane-based purification system. And EPA, Environmental Protection Agency, limit is 1 ppb, which means very small concentration is good enough to cause you a problem. Okay. So then there are methods. Obviously, we are not the first one to tackle this problem. There is a distillation, adsorption, degradation, and membrane separation. I think membrane separations are really, really good candidate for many reasons because it complements existing membrane technology, purification technology. But there is a challenge associated with it. So we used our membrane. Okay. We used our membrane. Okay. Here, when I say Ca1 and Ca2, in one case, we use different solvent. In other case, we use different solvent to prepare two different types of membrane. What difference it would make? The distribution of nanopillars would be different. Okay, just wanted to check, just to generalize this. But just to summarize the result, as you can see, this is the cellulose acetate, 100%. There is no nanopillar. And we keep on increasing nanopillar percentage. We went up to 0.8%, 0.8, guys. Okay. And then the flux increased. Obviously, there are nanopores that will help the increase of flux. And more interestingly, when we did the phenol removal, look at this 100% cellulose acetate, you have about 12% phenol removal. On the other hand, just by adding 0.8% of nanopillars, you can go up to 85% removal of phenol. Okay. So then obviously you have to check whether it works for all the conditions, pH conditions, but it's very important. And then also we did it with a different salinity because when you dig water, the mixture is high saline water. Okay, we have to check whether it's a working condition. As you can see, it works very well. And obviously we did it for 4 cycles for both membranes. The message here is we couldn't sell the first part, even though that work published in higher end journal, okay, relatively, but definitely we could sell this one to the company. Okay, so they started thinking that can we, of course, another thing when you're using cellulose acetate membrane, you can make a large scale membrane production as well, right? It's an existing setup. So that's where we are collaborating with the company. How does it work here? You have nanopillars within the membranes. Obviously, when phenol pass through because of the hydrophobic interactions and hydrophilic interaction, because OH and the phenyl group from the phenol that leads to the trapping of this phenol. When you do the back washing, phenol comes out and you can again reuse this membrane. Okay. So the next question we are asking around this 3D thing, as I said, when you saw that Engevante cover article, nice film, right? But if you ask me, are they mechanically stable? No, they're not mechanically stable. So if I want to really use these films or membranes, whatever you call it, in real life application, I need to have this mechanical stability. So what we tried to work it around the synthetic condition, but there is a twist. If I do the same COF and do the things, of course, I cannot even publish anything, right? So what we thought, instead of that, you remember the bromine linker? I introduced a linker here with fluorine. What was the intention here? We know fluorine can introduce hydrophobic interaction to something, right? So one of the intentions of using this linker is to use this membrane for PFAS removal, okay? Parafluorine sulfonic acid family, okay? So then we synthesize this, but in this case, we didn't synthesize as of like pristine membrane. We synthesize the film, and then we allow it to settle on pan membrane. Okay, so then the pan 3D COF membrane is quite stable now. Okay, so it is not coming etching out because of the supramolecular interactions. Of course, if you are interested in chemistry, as you can see, it's quite flexible. We can use it. It's not coming out or etching out anything. Then we used it for PFOA removal, the representative candidate of PFAS family. Okay, as you can see, the feed concentration we varied, the removal efficiency is very good. In this case also T1, T2 means the amount of time you are leaving for this film formation, it leads to the different thickness. Okay, so two different thickness sample we checked, and the one with the lower thickness obviously having the better result when it comes to the permeance. Okay, then that membrane we took it forward. Okay, so in that case, removal efficiency after 5 cycles, as you can see, it has almost close to 100% removal. Okay, even in very low concentration. And then, of course, we have to check whether it works for different pH. That's what we did. And also different salinity. We went from 0.5 gram per liter to 10 gram per liter. It's really a decent salinity, okay, to check with. And as you can see here, this is obviously marketing strategy for publication. But in any case, as you can see, the removal efficiency is close to 100%. Okay. And also permeance is very high. I think compared to many membranes used for PFAS, especially when PFAS result, if you see, most of them are used powders. If membrane literature, if you see, so I think this membrane is one of the best performers so far. Okay. Again, it's a marriage between the actual material, which is giving you some property, and also existing material. If I just go with the pristine membrane, maybe I cannot use it, and also it's very expensive, to be honest with you. Okay, so that is another story to talk about. Then again, I'm not going into details. We just want to prove how this PFOA is interacting with this membrane. As you can see, there is a fluorine interaction, obviously, and also there is a CO, the carbonyl group is interacting with the surface. How did you prove this? This is the XPS data, which means it's highly reliable and highly sensitive data. Okay. So then also we did some modeling study to understand whether these interactions are true or not. This is complementarity. Okay. This is theoretical. This is real experimental evidence for that. So just switching the gear just a bit from the water remediation to desalination. Okay. Again, I think this slides, I'm just putting it, I think you no need this introduction, but just to tell you, I think including India, most part of the world is really going through water stress issue, and it will go even worse, I'm sure. Okay. So the question here is, what are the commercial or well-established desalination techniques? Reverse osmosis and membrane distillation to some extent. Both are really energy intensive process. Okay. For a country like India, I think it's questionable strategy. Middle East still okay. They have money because they can get money from oil and put it into desalination. But for India, I think we need to find something called sustainable desalination. That's very, very important, guys. Right? So people are started looking into other techniques. one of the things people talking about is electrochemical desalination. What does it mean? It's the capacity deionization, basically nothing but electrosorption, right? So why do you care about this? Because it's really environmental friendly. Because if you think about reverse osmosis and membrane distillation, energy consumption plus a lot of side effects. I mean, side products, sorry. Okay. And then it's a very simple operation. It's a simple battery operation. I would say pseudo capacitor operation. And there is energy efficient. I will show you. Energy input will be 1.4 volt, very minimum energy input. And also, obviously, it has a decent performance. But if you look into the literature, you will be surprised. This is the first work targeting chloride. Generally, when you salinity means you have a lot of metal ions with the chloride, right? Chloride is the common anion. You have sodium, magnesium, potassium, so on and so forth. Chloride actually constitutes about 55% of the salinity of the water, but people are always targeting cations, not anions. Okay, I don't know why, but there must be a reason, right? So what we thought, can we really use our tunable nature of our COFs into target selectively chloride? Okay, that was the idea. Then we dig up the literature. There are some 2D materials and all, but they are mostly focusing either on cations, and also they have a problem with, the performance decay after some point of time because of the stability of the material itself in the salinity condition. Okay. So that was the question we asked. Can we use? Yes, what we did, we simply synthesized a molecule of, and we introduced cationic site. Why do you want cationic site? Just to attract chloride. But we are using methyl iodide. I cannot keep that. Iodide is more toxic than other, the pollutants. So I replaced that iodide with chloride. It's a simple ion exchange. Okay. Then we used this one to prepare electrode. When you prepare electrode, obviously you need conducting support, because I'm talking about electrochemical desalination. We used graphene oxide as a conducting support, and with the binder and everything, we prepared the electrode. Then we tested that in our in-house desalination capacity deionization setup. Okay. What happened? We used our COF with the graphene oxide as one of the electrodes, and other electrode is activated carbon. Basically what happens, one side cations goes, another side anion goes, right? So then we did different applied voltage. It's a charging, right? 0.8 to 1.4. When we reach 1.4, it's about 62 milligram per gram chloride remol. It's a significant number if you're working with chloride remol. Okay. I think the chloride remol only paper after this came in Nature Sustainability, I guess, next paper. Okay. So then if you look into the performance of our material, this is really a good material. It's performing better with this combination. And important thing, it has to work in wide range of salinity. It cannot work only in some range of salinity, right? We did a wide range of things. Okay. And then when you go more than 1.6 voltage, that's a good thing, because minimum energy input is always better. Okay. But in any case, we tested what happens because it's the electrosorption. Obviously, saturation happens after some point of time. Okay. Surface saturation. But most important data is this one. Remember, guys, this is such a straightforward and simple desalination. Charging, discharging, charging, discharging, adsorption, desorption, adsorption, desorption, right? It's a very simple method. Okay. So when we did it for 30 cycles, the retention is close to 99%. That dynamic reversibility of adsorption and desorption is the key. Okay. So that's what we achieved here. But this is a simulated condition, guys, simulated condition, just lab simulation. Okay. Does it work in real seawater? That is the question. That's why we took some local seawater. We analyzed the composition of that using the ICP mass and other techniques. And when you look into this, even with seawater, it is selectively removing chloride compared to cations, and surprisingly, another anion, very common anion, sulfate. This tells you two things. The structure is so specific to chloride in two forms. One is electrostatic interaction can happen between chloride and sulfate also. But the pore size of the material is good fit into hydrodynamic size of chloride compared to the sulfate. Okay, that is the key. So then we try to understand that, obviously, and then we did some DFT calculations to understand what kind of interaction. It's a straightforward, guys. The only two things, electrostatic interaction and pore size control. Okay, that's no rocket chemistry here. But just to tell you, the simple material can be utilized. If you're interested, please check into Engavante last year publication. I will share two more stories, I think, if you are not bored, because my talk title says remediation and sustainability. So I have to talk something about sustainability, even though desalination comes under sustainability, but I will go more deeper into it. Okay. So now, so far what we did separation, we did removal, right? That's good. But if you want to be sustainable, what do you want to do? You want to remove something which makes you money, which gives you money or which makes you rich, right? That's very, very important. If you can do that, what you can do, you can bring that money back into the system. That's called sustainable desalination or sustainable, whatever you call it, right? That is the key. So we call it as a back loop mechanism. We have to do that, okay? So we thought, can we use our method? We targeted a couple of very interesting metals. First one is palladium. Why palladium? Palladium is very, very important metal. As you can see, the consumption and recycling amount is very, very low, to be honest. And palladium is very well-known catalyst also, if you know that. I mean, people are using it. So if you look into the price and the application, what you can do with palladium is immense. But palladium price is more than gold price. If you go and check the literature, that's surprisingly so. Okay. So what we thought, can we recover palladium from the industrial waste? But industrial waste is very complex. You have so many other metals, right? Selective removal of palladium is the key, because if you want to reuse it, you have to do the selective recovery. That's where tunability of the material is key. If you use random activated carbon, what will happen? It will take everything, relatively. So what we did, we here introduced something called very interesting hydrazone linked COF. This hydrazone link is very, very important. We did bit of TFT studies before starting this work, just to understand whether it brings selectivity or not. Okay. So then we synthesize, we characterize. I'm not going into details, but look at this. When we use this material to adsorb palladium, palladium is coming to this, very nice, beautiful. The important thing is the selectivity here. Okay. It's giving over 80% of selectivity to palladium itself. And obviously this is one of the best performers then. We did it for 5 cycles. But the question comes, you recovered palladium, but it is still with my COF. How can I get back this palladium? Then only I can make money. And palladium is a very sensitive metal. If I get back, it becomes palladium 0, obviously. Right? So what we thought, instead of targeting palladium, elemental palladium, it's better to use it somewhere else, right? So when we use this, the good part is this linker is not only coordination linker, it is also a in situ reducing agent. Okay. So what happened? Whatever adsorbed palladium become palladium nanoparticle. Automatically nice, well and good. What can I do with this? Palladium nanoparticle with 0 oxidation. So obviously, I can use it as a catalyst, right? That too, heterogeneous catalyst. Usually, palladium catalyst used as a homogeneous catalysis. What does it mean? After reaction, you cannot recover. But in this case, you can recover, right? With the collaboration of your own institute, Professor P.S. Mukherjee, we did this, using this catalyst, heterogeneous catalyst for CC coupling reaction. Two things are important, guys. Look at the concentration here. 0.5 molar percentage concentration, very low concentration. We could see 99% conversion into CC coupling. Okay, this is another thing. From waste, we got palladium, and we are using it for the catalyst. Okay, it's a waste to wealth kind of concept. Okay, that is one of the stories. Then obviously we have to do the recyclability, because if you're using only for 1 cycle, there is no point, right? So we used it for at least 3 cycles, and also we analyzed the product's purity and so on and so forth. The second waste we targeted is e-waste, because as you may know, especially young country like India, younger generation likes gadgets, right? Or electronic stuff. So electronic waste will keep on increasing, right? But electronic waste, the good part is it's a source of a lot of good things too, waste. So there are methods to recover some metals out of this electronic waste. One of them being cyanidation, cyanidation. It's a very toxic method. And another one is hydrometallurgical, because as you say, hydrometallurgical is energy intensive process. What we thought, can we use adsorption or electrochemical method? Just because low energy demand, kinetics can be improved, efficiency can be improved. But again, guys, bringing selectivity is the problem here. Okay. So then what we did, we introduced a new group called benzoxide-based COF. It's a chemist within us. It's a multi-component reaction if you're interested. So the idea is to introduce this flexible core within the framework. Why? Because it is very selective to gold. Okay. So then we use this COFs to recover gold from e-waste. Okay. Because the price, gold price going very high. So it's even better target now. Okay. So then we did in the different pH. The good part of this is it is working very well in low pH. Do you know how we digest the waste? We digest it in an acidic solution. One of the problems with all sorbent people use, because it's highly acidic solution, after 1 or 2 cycles, it will die. Material itself will die, decompose. Okay. And in the low pH condition, it doesn't work most of the times because of the protonation, because of the functional thing. The good thing is it works very well in low pH. Okay. And also you can take about 3.2 gram per gram, 3.2 gram of gold per gram of COP recovery is possible. And look at the selectivity with these competitive ions. It has close to 96% selectivity to gold. That's the kind of tunability. But again, this is simulated condition. Okay. What we did, can you do it in real condition? We took some CPU, waste CPU, we digested it. Obviously, we removed the solid part, right? And then we took the solution using the ICP. We analyzed the composition. As you can see, very small portion, 0.5% of gold being very expensive metal. We are interested. Otherwise, this is nothing, right? So then now we have a system. We can recover copper separately, nickel separately, gold separately in systematic way in one pot system. Okay. But in any case, initially our target was gold. And with this complex situation, we could achieve close to 100% selectivity for gold. Okay. But again, this is publication. Don't worry about it. Just to show we are the best, right? But most of the time, that's not true. So my point is, this is adsorption again. What happens now? What is your interest? Elemental gold, isn't it? But adsorption again problem, the adsorbed gold become gold nanoparticle. Getting back into elemental gold is a problem in real general adsorption. So what we thought, instead of adsorption, can we go to electrochemical? Why? What is the use of electrochemical? You adsorb, get back into the system, dissolve, charging, discharging thing, right? So for that, we used CDI. Okay. I cannot show the structure because it's with the industrial patent and spin-off. I will talk about it. So I cannot show the actual structure of the COF. But what we achieved so far, as you can see, is with 1.4 input voltage, you can achieve uptake efficiency close to 100% selectively. And also, it works very well in low pH, well and good. And this is actual recovery. You can see this is the electrode and this after recovery of gold. And surprisingly, you can get 5.1 gram per gram of gold. Why this is so important? Because it has to be economical, right? You should understand. So this is the, I think, highest record now. Okay, we have that. So that leads to, okay. Then we did with a complex situation here where you have a lot of metal, still we could achieve really selective recovery of gold. That led to a spin-off from my group called Regold and got some award. Because of this, they gave some money to scale it up. Now what we are doing, we are scale it up, but most interesting thing, just I think before I took flight from Abu Dhabi, 2 days before, my PhD student come with lot of small gold balls, elemental gold balls into my office. I told her, please keep coming. Okay, come very often. It's very important. So now we have a technique. We can get real elemental gold from e-waste. So what we are doing, we are collaborating with the local municipality because they are the one collecting a lot of waste and everything. And we are getting waste from them. Obviously, we promised them we will make you rich. So hopefully, I think it will be translated. Maybe if I come back here, hopefully, I think this will be translated into real thing. We also did some techno-economic analysis. You can ask what is the cost of COF, what is the gold you are recovering. We are kind of in a good shape now. So that's why I wish I could show you the COF. It's a very cheap COF. Okay. So in any case, this is another story. The last story, just to talk about last only 2 slides, I believe. Another important waste in my place and also going forward, if we start increasing desalination in India, one of the problems is the waste created by desalination is brine, not brain, but brine, right? So the brine issue is, brine is good waste, but it has a lot of good things also. Brine, one of the good metal within the brine is lithium. I don't think I need to explain you why lithium is important because we're talking about lithium batteries, so on and so forth. Okay, right? But do you know percentage of lithium is so minimum compared to sodium, potassium, the competitive ions within the brain? And also it's being a small atom. Selective recovery is even more difficult. So what we thought, can we use our strategy to introduce the heteroatom distribution within the COF? And this one, because of the electrostatic interaction point variation and the pore engineering, can we get selective recovery of gold? That's what we did in electrochemical lithium recovery. We used this material as an electrode, and we could recover in different salination, saline water, about 15 milligram per gram. This is not a great value. It was published in a decent journal because it was the first time someone used COF for electrochemical lithium recovery. But now what we have in lab, we could go up to 600 milligram per gram with the selectivity factor close to 200. The most important factor is the selectivity factor, is between lithium to potassium, lithium to sodium, lithium to magnesium. Okay, so that's again under patent. So I don't want to show that because we have a restriction in my institute. If we applied patent, we should not present those data. Okay, so in any case, this is just to tell you these materials are not a bad candidates to look into, right? We can tune them. So just to summarize everything, I hope in last 50 minutes or so, I convinced you guys, COFs, of course, conjugate MOFs I didn't show you, but there are so many interesting applications, are tunable. Retro approach, what does it mean? I think generally researchers, what we do in generally, we synthesize some material and we ask somebody to test this application, that application, whatever application works, we make publication. This is a classical approach. Okay, I think we should come out of that. What does it mean, retro approach? If you're an organic guy, you know what is retrosynthesis. You start from end and come back. Okay, so retro approach is, if you go to a doctor, what will you do? Doctor give you medicine first and then ask your symptoms, or they ask your symptom first and then medicine? So I think you should sit with the guy, if it's a medical guy, industry guy, doesn't matter who, water guy, sit with them and ask what is their problem. And then come back and utilize your skills to do the molecular engineering. That approach is really, really effective. It's a hard because you cannot find the solution to everything, but it's really good approach. So in my lab, I think our important thing is retro approach to fit to purpose kind of applications. Okay. And molecular to bulk level, as I said, we are going from small thing to now spin off and doing large scale thing. It's feasible, but in not all cases. I was very honest. Some of the materials good for publications. You cannot do it beyond that. Okay. Right. And then scalability is definitely work in progress for COF. Okay, so there are some COFs, very few COFs, you can make it in ton scale. Most of them are still in milligram scale. Okay, so this is a work in progress thing. With that, thank you, but I think I need to do some editorial duty. So being part of this journal, I'm editor of this chemical engineering, and also I'm in editorial committee of other journals. If you happen to submit anything, obviously, I think you guys are very relevant to chemical engineering journal, I'm sure. So if you happen to, I will be happy to handle, and please don't forget to assign my name. No reason. Okay, with that, I conclude my talk. If you have any questions, I'll be very, very happy to take it. Thank you so much.
So why PAN, not like PPDF or something else? Any
Um, to be honest, PAN was just because of the availability in the lab. Okay, just to be brutally honest, in my place to get another membrane, I may need to wait another 4 months. It's not like India, you get quickly.
so it's not about like some functionality.
No, but no. Okay. There is another reason. I think not only pan membrane, we tested some other, but the compatibility of our COF with the surface of the membrane is the key. Otherwise, what will happen? Slowly, either just powder deposition happens or etching happens. I think it had a very, very good compatible or stable sticking is the pan membrane. That was the reason. Obviously, we didn't try all the whole spectrum of different membrane. That's why I said I cannot answer you whether pan is the best candidate. I don't know. Within the tested cases, so at least 4, I think 4 or 5, fan is still okay.
And another question is, like you mentioned about the self-standing member, like how stable they are, because you used it for some dyes and some boil water.
No, I think during my presentation itself, I'm very vocal about it, right? Those membranes, the one used for demulsification and the one used for dye, those membranes are not a good candidate as a standalone pristine membrane for translation. That's why we used same COF as a nanopillar in cellulose acetate membrane. That is more practical. So being in chemistry department, what we do fundamental science to understand new chemistry and then do the translation. So all the membranes, whatever I show, pristine ones are academic interest and in early stage, I would say. But all the membranes, we go with the hybrid approach, either with the cellulose acetate or PAN or whatever, they are more practical. And being an engineer, maybe you may like that part, not the first part. But being a chemist, I like the first part because it leads to a higher end publication.
Actually, how did you like do the filtration with that membrane? Like
No, that much stable. Oh, 100%. So it's not like you cannot know. I showed you the pictures, right? I mean, you can hold it, but I'm saying for long term stability is the issue. Mechanical. Yeah, even flexible one. So you can do that. And also you can go the dimension, also good dimension. You can 5 centimeter dimension, we can go. That much pristine membrane growth is very difficult in power. That we can do. But if you ask me, can you really use it in real life application? Maybe not. That's why whatever cycle we tested, it is stable. No doubt, it's not breaking, no physical break. No. No. Yes, we did it with the powder. In that case, maybe for a normal column, powders are better candidates. So we did it, for example, we have a different type of cork. Maybe one is very good for particular pollution. Another one is another pollution because one adsorbent cannot do everything. So then what we did, we stacked them. Okay, I'm not showing that, but we did it for micro pollutants, pharmaceutical removal, because especially we were targeting a lot of this pharmaceutical pollutants within the water. But that is 4 years ago. So I wanted to show a fresh data.
a couple of and one this PFAS actually. So how are you taking care of the like the dispose after your experiment? How you are taking care of these? So I think yeah, how you are disposing the PFAS?
The idea here is in our case, because it's 100% taken by our adsorbent, it is within the adsorbent now. We are not taking it out. But even then, the amount of the concentration of solution what we are using is a very, very low concentration. And in our place, because Khalifa being because water is a big area, our country. So we have a very specific way of discarding these. And we have to put it in a certain place after our all this decanted solution, and they will take it somewhere. I'm not discharging it to tap or somewhere. No. No, that's what we did a backwash. That's why multiple cycle we can do. Backwash we do. But at the end, the whatever, I mean, if you're talking about discarding completely, yeah. So then, hey, that one we have a specific EHS department to take it.
And the last is like yeah, the COFs are like fantastic material, but how do you see because these monomer itself are very costly. So water application because I am also using the COF, so the monomer are itself very costly.
Because I mean, don't get me wrong, but I'm a very optimistic guy. If you go back 15 years ago, if someone asked India will have a train run by hydrogen, would you believe it? Would you believe it? I wouldn't. But today train is running, right? So what the message what I want to deliver is when I started COF 8 years ago, people are not even synthesizing gram scale. Today, in China, there is a company, it synthesizes only COFs in tons, and they use it as a beads, COF beads for water purification and gas separation. But what they are doing, something called melt polymerization. Obviously, it has limitation. Only some of the COFs you can scale it up. But I'm not so surprised. In our lab now, some of the COFs, we use mechanochemical preparation without any solvent. We can synthesize half a kilogram of COF inside the lab. Not all COF. But obviously, as I said, it's a work in progress. And if you see the field, it's how many inches? Very young field. So in my opinion, the day will come. And another reason, as you mentioned, one of the issues with COF cost is associated with starting material. Why that is expensive, tell me? Because you don't have end user. If end user amount increases, when COF applications and real translation increases, then there will be a buyer. Now I have a friend who graduated from NCR. This guy, his only job, he started a company. Because he came from Rahul Banerjee group, they work on COF. He is synthesizing only one. It's called TP, fluoroglucinol. Aldrich sells 1 gram TP for 2,700 US dollar. This guy sells me 20 gram of TP for 40,000 Indian rupees. Still expensive. I think in India he is selling it for less. For me, because abroad he is selling 40,000. 20 gram, 40,000. 1 gram, 2,700 signal. So when people find the end user, because TP is very well used in COF synthesis, right? He started. When people start using more and more COFs, and if one or two hit application comes in real translation, then the monomer synthesis guys will wake up. Custom organic synthesis people will start like anything. Then obviously cost will be increasing, right? And another thing you have to understand, I always say this, it's a trade-off. You can buy a bag for 100 rupees and you can buy a bag for 1 lakh. Both are bags. You cannot put, you have to put whatever you have to put, right? But people still buy 1 lakh bag. There is a reason for that. You understand? So I think it's a trade-off. So I'm not saying COF will solve all the problems, but some of the niche applications where COFs are beautiful, because especially the selective recovery, selective removal, selective separation, COFs are beautiful candidates. One of the problems, what happened, even if you go and check Omar Yagi's work now, he was working entire life MOF. He got Nobel Prize. From last 1.5 years, check, you not even a single work on MOFs. Even the company he started for MOF for CO2 recovery, direct air capture, what they realized after 3,000 cycles, because you have a humidity, right? MOFs are hydrolyzed. So he is getting into COF now. Because sometimes this framework, how many choices you have? COFs and COFs now, maybe until we come up with some new framework material. So I think very positive, being positive, maybe hope in my lifetime, it will be a big thing. And what I discussed with, the Omar Yagi himself, he is expecting even COF to get another Nobel. That's why they separated MOF from COF. Okay, so I'm not selling because I'm working on COF. I'm working on polymers also. Today, if you ask me for a translation scale-up, polymers are better candidates. But for very niche and selective applications, COFs are better candidates. But they are still in academic level. Thank you.
Very excellent talk.
Thank you.
A lot of molecular level engineering for MOF and COF and all that. So I have a general questions like for resources recovery aspects. So for your point of view, which treatment technology is the best choice? Like the adsorption, electrochemical synthesis, electrochemical separation, or the membrane separation for full scale, like sustainability aspect, like removal, resources recovery, and again, cleaning of that material, all the aspects. Which one?
Thank you for the question, but I wish I have an absolute answer for that. I think there is no absolute answer for that. Because I think it depends on what metal or what target you have. For example, there are some metal, people say precipitation is better than all whatever you mentioned. Okay, now there is a company in Saudi Arabia, a big company. They recover lithium from brine, just precipitation. That guy is super rich, flippingly. So we are working on electrochemical and other things. So it really depends what's your end purpose and also what is the target. But still, in my opinion, if you can recover elemental form in adsorption, I think adsorption is a better candidate, because it's a less energy intensive process, if you think about it.
The problem is it gets absorbed on some material like
Yeah, then you can dissolve it if
dissolve
you
it,
can.
but it will go come into the water media or some media again.
Of course, but it's a very selective. Only one metal comes. No, then you can recover. That is not a big deal. You
Yeah,
can
so in
precipitate
this
it out easily. But when you have a mixture, precipitation, selective precipitation is difficult. But it's only one metal, you can get it into any form. That is not a problem. But the challenge in adsorption is getting dissolved in elemental form. That's why people are not using it. But I think what we are seeing, electrochemical, not many people are exploring. So that's why we are getting into that avenue. I think, in my opinion, electrochemical, if your metal is stable under potential, the target metal, it has to be stable.
Yeah.
So electrochemical is really good one. Why? Think about it. You have a CDI setup. Now we are asking a Singapore-based company to have a stacked setup. You can have multiple stacking together. And it's a multi-scale. You understand? Charging, discharging, charging, discharging. Even you start with, say, 1000 ppm. One cycle, it becomes 600 ppm, 500 ppm. You understood? So in one go, you can do that. And then very easy, because desorption to the solution, backflow. So in my opinion, if you ask practical easiness, I think electrochemical. But as I said, again, if you can recover elemental form in adsorption, it's very simple, because you just run through the column, right? And also scalability is easy. You just get into anything. Maybe electrochemical still work in progress for scalable, big volume, right? So it's subject to subject. Every method has its own pros and cons. But I think if someone can optimize one method for one or two metals very selectively, I think that's good enough for them to make money.
Recently, we start working on selective separation of lithium using membrane. Yeah. So we use crown ether, not the COF from MOF. So yeah, the complexity is in making that crown ether.
Got it.
But yes, so that we also working on absorption part. So main struggle is dissolving the material.
You cannot. That's why when you said
again,
crown ether, my face was different, right?
Yeah, so that's why asking. Okay, thanks for your insights.
Crown ether, good for academic publication. I'm very honest.
Sure.
If you want to translate it, because you cannot get it out, because lithium sits so beautifully inside that crown ether cavity, it doesn't want to come out.
There are some, crown ethers, or maybe you can functionalize some crown ether, which will give the free volume to the lithium so that it will pass through only. It will not.
Can that is not real adsorption.
No,
that is a diffusion technique.
Yes, that is for membrane diffusion.
Yes, a membrane diffusion technique. If you can do membrane diffusion technique, again, the science paper published by same guy, Zipping, they use these diffusion techniques to pass only. In that case, these kind of materials are beautiful, because you can control the diffusion pores.
Exactly.
You cannot do it with other materials. So that's why I'm saying this is a niche application. In that case, you no need to use entire membrane core. You upper layer, if you have a technique, I think he has a very nice technique, right? Engineering technique. Upper layer you coat with the copper MOF, but the key is alignment. If you can align nicely with the membrane, it's a good thing.
Thank you.
No problem. Hope I'm not taking too much time. Okay.
Hello, sir.
Thank you.
It was very nice talk. My first question is, have you tested your COF membrane with the real wastewater or synthetic feed? Or have you performed pilot scale study and where LC and T analysis was there?
Maybe I think you're coming from process engineering background, I believe. Good question, but I think I answered most of that because we are still in a small scale. So forget about pilot scale. But the real mixture, yes, we did it. Especially for phenol removal, we took a industrial phenol, the real wastewater only. Okay. And PFOA, we did simulated condition. Desalination, we did it with the real seawater. So subject to subject.
My second question is that what is the biggest challenge in the scaling of this COF membrane?
I told you many things. One is starting material problem, cost. Second one is when you go from a gram scale or milligram scale to multigram scale, maintaining the crystallinity is the challenge. Remember, when you get the crystalline polymer, I don't know how many chemists here, it's a kinetic product. General polymer chemistry works with thermodynamic product. So kinetic trap needs a very specific condition. So translating from gram scale to kilogram scale, that is the challenge. So we are into some of the COFs I said we can do it to 500 gram scale or something, but most of them are in 500 milligram to 1 gram scale. Yeah, I hope I answered your question.
Yeah.
Thank you.
And how do your membrane resist fouling during long-term operation?
We have not tested fouling, my dear, because fouling comes with multiple cycles. For that, we need to have a real translational membrane. Okay, we are not there yet. We are not there yet. Because when you do 4-5 cycles, there is no fouling. And also fouling comes with a real complex mixture when you take, right? Like municipality waste or something like that. We didn't do that yet. So I don't have answer for that.
Yes, sir. And my last question is that can this COF membrane be integrated with existing reverse osmosis and nanofiltration system for high-tech water use application?
I missed your first part.
Can this COF membrane be integrated with existing reverse osmosis and nanofiltration system for high-tech water?
That's exactly CDI can do. Because CDI, please remember, I think I missed that point, guys. Capacitive deionization cannot be used for real saline water when salinity is 10,000 ppm or 20,000 ppm. Because electrosorption, it will be saturated with no time, boom. So it can be used only if salinity is lower than 1,000 ppm. So what proposal we are giving to the existing, the membrane-based desalination plant, because usually you have a stages, right? Last stage, when salinity comes to a level where we can handle CDI, let's put CDI because it's less energy intensive, right? So the amount of energy you needed for one more cycle of desalination can be reduced. 1 or 2 more cycle of desalination can be reduced into CDI. So that you are not entirely cutting the cost, but you are cutting the part of the cost. It has to be combined because CDI will never be used for a real high salinity water. No.
One more question, sir. I
Yeah.
am stepping into modeling thing. So which kind of model you are using for the CO?
We do material studio. I mean, for the structural simulation, yes. For other calculations, we use classical DFT or MD.
Thank you.
I'm glad. A lot of questions, unless I'm taking too much. Yeah.
Thank you for your talk. It was very interesting. I have very small doubt. When you used your COF as a nano filler in cellulose F8 membrane, was that membrane means the filter paper that you used? Did it become brittle again?
That's why the key is the amount or percentage of nanopillar. That's why you saw some result, I think. When we move from 0.8 to 1% or above, segregation started to happen. These nanopillars start to segregate within the membrane. So then membrane, the lifetime or membrane quality is gone bad. Of what? Size aspect ratio you're talking about. I think it's a micrometer size. You're talking about nanoparticle itself, right? Yeah, it's a micrometer range. 0.8. But it's, if you see the microscopic images, the distribution is very random.
Yeah, actually, I'm trying the same thing.
Yeah.
So the problem that I'm facing is the cellulose paper. It is becoming brittle. So I have done various loadings. Like maybe we have to do slow.
I think I can connect you with the student who worked on this. If you really want, I mean, I don't need any credit. Just I can connect you. And maybe if you have some common discussions because of the methodology exactly she used in the lab, it may help.
Thank you. Thank you.
Hello, sir. Thank you for a very informative talk. So, you already answered one of my questions. So, there was a figure B, the graph showing the loading percentage versus the capacity removal. So, 0.8% was showed the best out of all.
Optimum.
Yeah. So, when you moved to 1%, it was.
Yeah, aggregation.
So, the second, that was my question, one of the question. The second question was like the palladium that you used for catalysis. have you tried the removal of it? Like for the gold you have done. Like for gold you have done the recovery. From the COF you have.
No,
Huh.
no. Palladium is a tricky metal. It's very, very active metal. It's a gold is stable metal. That's why you can make jewelry of gold, not palladium, right? So palladium, I don't think anyone did it with this adsorption recovery. That's why people do precipitation. Still, it is in the counter ion form. Understand? So
Also the synthetic, I am a synthetic chemist, so
good.
like how difficult was the synthesis part of it? Like did it take a lot of time to come up with the
I think synthesis difficulty is a relative term, right? So I think I have been working in this area for some time now. I would say it is not so difficult because if you have a proper design principle, that is the key. If you have a proper design principle, 10 out of 10 will be calm. If you just have a random combination, 10 out of 10 will be polymer, just amorphous polymer. I can assure you that. It's just a combination. You need to have that what you called topological understanding, the structural topology, how it works, how it connects. So and also you should not go with very complex chemistry when you come to COF, because if you use very complex synthetic chemistry, there is no way you can connect dots for long range. You understand? So it's again choice. I mean, but for example, imine condensation reaction, hydrazone chemistry, these are all very well established chemistry. Keto, enamine chemistry, they're all very well known chemistry.
thing?
Uh-huh. Good.
The phenol one, you use the nanofillers. You said something about 4 to 5 cycles. Do you have like exact data as to how much cycles you can use it before it degrades?
I don't. But what we did now, we gave this the large dimension membrane. Actually, we can do it roll by roll, roll to roll kind of big membrane. We give it to a local company who are doing this water treatment. We don't have data because usually company people don't reveal data until last minute. So I don't have data.
The other thing was
Mhm. And you have to compromise on flux, right? Whenever you think about water application, two things are key, right? Permeation, permeance, and flux are very, very important thing. So when you do multi-layer, that's why we were controlling thickness of the membrane. Because when you go into too thick, then it may absorb very well or separate very well, but it's very slow. So who wants to use that, right? So it's a trade-off. So we have to see case by case, but trade-off. Yeah. Align. Yes, that's what we are trying now. But for that, you need to have a seeding point within the membrane. So you have to make a functionalization of the membrane. You should start COP synthesis from that seeding. Then you have control. Still, you cannot control 1D channel. So whenever I go to COP society meeting or anywhere, this is my question. If anyone come up with a strategy where they can, this is very important for engineers, where they can control the alignment of these COP or MOF channel within the porous support, it's a big breakthrough for a translation. Because nobody, we can claim in nice picture, always here and there. Retro, yeah, retro, yes.
Yeah, precipitation.
People do selective precipitation. No, but now what we are doing through our electrochemical thing, we are stepwise in the same mixture. We are stepwise recovery, like gold, copper. I think so far achieved gold, copper, and palladium we did, and iron we did. I have a very good lithium separation method. This is very tough.
You mentioned,
I can hear you.
yeah, you mentioned briefly about pharmaceutical products. Um, so are you looking at recovery or removal? And you know the decomposition does the after the removal, you see decomposition of the pharma.
What we did, what we are doing now, before we just remove by adsorption. What now we are doing, like for example, antibiotics or some hormonal drug, we adsorb on a system. Because of the tunability, I can use this system to adsorb and degrade. So we are using photocatalysis to degrade. Degrade to that level. Sometimes what happens, you degrade. Degraded product may be more toxic than actual product, right? So we are trying to make sure almost we are mineralizing it. Understand? So that is the thing, as one of the projects ongoing thing. We use this photochemistry to do that. But for that, it's very important. You need to adsorb first, then degrade, and we are doing it. I hope soon we will see some. Thank you so much. I really enjoyed a lot of questions. Thank you. Thank you so much.